So please maybe for a minute or two just go through whatever we did in the last class. If you have any questions, you can actually ask. So are there any questions? So if there are no questions, then let me start. So last class I discussed about actually no frame element. So and I gave of course some problems for you to solve. I'll discuss one example on use of frame element for solving problems. So the example, I'm not going to take one of those examples which I had given. Those are for you to solve. Of course, if you have any difficulty, you can always ask me. So let me take a somewhat simpler problem. So let us say that we have this frame and which is fixed at two ends here and here, and the loading is, let us say that there is a uniformly distributed downward load here like this. And so let us say that this intensity is Q naught, and here there is also a distributed load which is uniform. For the simplicity I'm taking it to be uniform. Although this can be also solved using Castigliano's theorem. You calculate reactions and then you can calculate bending moment, axial force, shear force at any location, and then you can calculate stresses and so on. But we want to look at how we can solve this problem using frame element. So let us say that the vertical and horizontal members are identical. So the length of this is, let us say, L, Young's modulus is E, cross sectional area is A, and I about Z axis is I, and same thing for this. So that is length is L, Young's modulus is E. Although they can have different properties, even within them there can be variation in properties, but again to simplify the problem I am taking this. And say although for more accurate solution you might have to discretize this into more number of elements, but let us say that no, we want to just discretize the whole thing into two frame elements. So the frame element which we have already discussed. So let us say no, this is global node number 1, this is global node number 2, and this is global node number 3. So that means this member we are discretizing just into one element, and this we are taking as another element, say element number 2. And this is a discretization. And typically now if you look at the element coordinate system, so for this element, usually the x-axis is from first node to second node. So let us say that its starting node is 1, global node 1, and the last node is global node 2. So then its element x-axis would actually be like this, and I want to keep the z out of the plane, so then y would be like this. So this is the local coordinate system for first element with origin at first node, that is, which is global node 1. For the second element, let us say that this is the starting node and this is the last node. So for this element, the local element x-axis would be in this direction, say that is your x, and again keeping z out of the screen, you take that this as y, so that if you rotate x about positive z axis you get to y. So as you see here, for this element the orientation of the local element x and y and local coordinate system for the second element, they are actually different. So we need to transform. So we need to decide what is our global coordinate system. So let us say that the global coordinate system is, let us say that this is my global x-axis and this is global y-axis here along this, and z is of course common in all cases. So as you see, the first step would be to transform this element level governing equation. So as you see, as far as the second element is concerned, the local element coordinate system x and y is actually parallel to global x and y, that is small x and small y. Whereas for the first element, local and global coordinates are different. So we need to transform the equations for the first element. So let us look at first element number 1. So when you look at element number 1, now what is the angle between global x and local x? 90 degrees. So alpha is, for the first element, is actually 90 degrees. So the transformation matrix for the first element would be, what would be the transformation matrix? Only you are going to put the value of alpha. So what would be the transformation matrix? We had already defined that in the last class, isn't it? So this was cos alpha sin alpha. So it is going to be cos alpha is 0, sin alpha is 1, because alpha is 90 degrees here. So 0, and then of course we have these zeros. Then the second was minus sin alpha cos alpha. So you will have here minus 1, this is 0, and then the rest of things, these are 0. Then the third row was 0, 0, 1, 0, 0, 0, and then this is 0, 0, and then 0, 1, 0, and then this is 0, 0, 0, minus 1, 0, 0, and the last one is 0, 0, 0, 0, 1. So this will be your transformation matrix with alpha equal to 90 degrees. This was defined in the last class in terms of alpha. We are just putting the value of alpha, right? Okay. Then now the transformed stiffness matrix really is going to be T transpose into KE into T. So we had also looked at what is KE for frame element. So if you, I think all the intermediate calculations I am not going to do. So you have KE, which was done in the last class, and now the T is defined. So if you do this, element level transformation, what you will get is the transformed stiffness matrix. So I am going to write the final result I have worked out. You can cross check it. So first do T transpose into KE and then into T, or KET and then pre-multiply by T transpose, whatever you want to do. So if you look at this transformed stiffness matrix comes out to be, if you do this for the T we have defined, and so the final result is, you have to do those multiplications intermediates. So finally what you get this as 12 EI by L cube, then 0. Let me write this. So minus 6 EI is it readable if I use the final this one? So minus 6 EI by L square minus 12 EI by, is it readable, this final? So this is 12 EI by L cube, then 0 minus 6 EI by, so after the transformation this is what the first row would be, L square, and then the second row is 0 EA by L 0, and then minus one more 0 here, 0, and then minus EA by L 0. So this is the result of this multiplication. This is what you get. And then third row comes out as, you can cross check, minus 6 EI by L square 0, and then 4 EI by L. See, alpha, if it is different from 0 and 90, then you could get this as more complex, combination of terms, but since alpha is 90, so you simply get again in this particular form. So this is 6 EI by L square 0, and then 2 EI by L. So this is the third row. Then the fourth row comes as minus 12 EI. Of course it is symmetric, you can check. So L cube 0, 6 EI by L square, 12 EI by L cube 0, and then 6 EI by L square. Then this is 0 minus EA by L, 0, 0, EA by L, and 0. Then the last is minus 6EI by L square 0 2EI by L 6EI by L square 0 and 4EI by L. So this is what you get here as your transformed stiffness matrix. Actually, you now you would see that although this we are getting mathematically directly, but if you see some correlation with the coordinate axes. So see, local x is actually aligned with the global y, and local y is aligned with negative direction of local x. So accordingly you will find that now since the axial direction is actually global y, so the axial stiffness terms have gone with the second degrees of freedom. Degrees of freedom, no, first the displacement along x, then second displacement along y. So here correspondingly if you look at your DE, the element level vector of elemental degrees of freedom in the local coordinate system is u01 v1 theta 1 u02 v2 and theta 2. So where u01 is the displacement along capital X axis, v is the displacement along y axis, and theta is of course is the rotation about z axis, whereas the vector of elemental degrees of freedom with respect to global coordinate system, this capital DE, you are taking u1 displacement along global x, then displacement along global y, and then rotation, and then the same thing for the second node u2 v2 and theta 2. So see, now if you see the displacement with respect to global y axis, that is along y, small y, is actually the axial displacement, and axial displacement in the elemental degrees of freedom vector with respect to global coordinate system is sitting at location 2 and phi. So you see the stiffness, axial stiffness is now going to location 2 phi here. That is second row, second column, second row, fifth column, second row, and fifth column, fifth row. So that is how you know from the transformation it automatically comes out like that. And then if you look at the the bending, now if you see the transverse global y axis is belonging global you can say global x axis is along negative local y axis, which is a bending direction. So you would find that there is a this term is of course the diagonal terms remain positive, but you would see that there is a change in the sign of this. So originally if you look at the first row and second column of the just bending stiffness, this is actually plus 6EI. So if you see that is actually 6EI by L square. Since the global x axis is corresponding to negative of local y axis, so you get a minus sign here, then you get a minus sign here. When you look at in this, you will find that again the change in the sign. So if you see this stiffness term, the second row of the simply if you look at this was 6EI by L square, now you have a minus sign because the local y axis is in the negative direction of global x axis. So but the rotation is same, the z axis is same, but there is a local x axis, y axis is along negative global x axis, and that is why there is a change in the sign also. So you can yourself study that how the stiffness terms are getting redistributed in the transformed stiffness matrix, and the changes in sign because of this particular change in the direction, this being in the opposite direction of the local y axis. So wherever the displacement and the force, the minus becomes plus, but displacement and rotation would be plus minus minus. Similarly, moment and displacement would be plus minus, so equal to minus. Moment and rotation would become minus plus. So these relations you can actually yourself. I want you to look at which of the signs have changed and which ones have not changed, and why they have not changed and why they have changed. That you can look at based on the coordinate directions I just mentioned. So this is as far as the transformation of stiffness matrix is concerned for the first element. Now similarly, if you look at the external load vector, so if I look at F external for the first element, so we need transformed external load vector would be T transpose into F external is equal to, I think it's still using the bigger one is better. So if you do this, what is the F external for the first element? What you have is only load in the local y direction. That is let us say that this magnitude is also q naught. So actually this, of course, here you will have T transpose, which we have already defined, and in the local system this load vector is going to be along the local x-axis. There is no force, distributed force in this direction, so qx is 0. What we have is qy, which is equal to q naught. So the load vector would be in the local coordinate system 0, q naught into L by 2, q naught into L square by 12, then 0, q naught into L by 2, because it's a constant and we have the same shape functions. So this is q naught L square by 12. So this is what you have. This is the load vector in the local element coordinate system, and once we pre-multiply by T transpose, we would get the same thing in the global coordinate system. So if you do this multiplication, T transpose, T already defined, you take T transpose and multiply with this. So finally this comes out as this load vector you would find comes out as minus q naught into L by 2, then 0, and then we have q naught into L square by 12, and then again minus q naught into L by 2, 0, and minus q naught into L square by 12. So this would be the transformed load vector, external load vector for the first element. Again you see, because the local y-axis is along the negative global x-axis, so we have these forces going here with a minus sign, which are no positive here. This is the force along global local y-axis at node 1. This is the force along local y-axis at node 2 of the first element. That is here, q naught L by 2 here and q naught L by 2 here. But since when we are transforming that to the global system, because our global x-axis is along negative y direction, so you get this force here. Now see, this force is shifted to the first location with a minus sign, and this force is shifted to the fourth location with a minus sign, and then this remains 0, because now the global y-axis is corresponding to local x-axis, which is the axial direction, and in that there are no distributed forces, so these are 0. But the moment is about z-axis, and z-axis orientation is still remaining the same. That is, if you see here, your z-axis is whether you take this local x, this local y, z is like this. For the global x and y also, z is the same. So the moment is about the same axis, its sign remains same thing at the second node. So the moment is still the same sign, that you have basically this moment q naught L square by 12, and this is minus q naught L square by 12, which remains here also, q naught L square by 12 and minus q naught L square by 12. So this is the transformed stiffness matrix of the first element. Now if you look at the second element, for the second element, your alpha is 0. So when you put alpha equal to 0, you will find your transformation matrix T is actually going to be identity matrix. So you will get the same transformed stiffness and load vectors, because cos alpha, sin alpha 1, 0, 0, 0, 0 you will get, then minus sin alpha cos alpha, which is again 0, 0, 0, then 0, 0, 1, 0, 0, 0, then this is 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. So this is identity matrix. So for the second element, the transformed stiffness matrix would be same as what we have in the local coordinate system. Reason is that the local x-axis is parallel to global x-axis, local y-axis is parallel to global y-axis. So we need not do that multiplication again. So now next is assembly. So when you look at the assembly, now after the transformation only we are going to do this assembly. So let me write that in the next page. So here let me say first is the stiffness matrix. I hope I can fit within the available space here. Then you will have load vector due to external forces and internal load vector. So this is going to be the structure of the transformed finally assembled system. The degrees of freedom now in terms of global coordinate axes are going to be displacement along the global x-axis at node 1, displacement along global y-axis at node 1, then the rotation about global z-axis, say theta 1, then node 2. Node 2 is global node 2 is here, this is global node 2. So now take this the corresponding degrees of freedom for the second node, so which is u2, v2 and theta 2. Then for the third node, u3, v3 and theta 3. See, these displacements are with respect to global coordinate axes, small x, y and z. Now if you look at the connectivity of the first element, it is defined between global node 1 and 2. So yeah, its contribution will go to the first. So if you look at the rows and columns here, so the rows and columns are say this is let me put here column number 1, then here you will have 2, 3, 4, 5, 6, 7, 8 and say 9 here. And similarly the rows would be of course defined by these themselves, no u1, v1, but let me write. So this is row number 1, row number 2, 3, 4, 5, 6, 7, 8 and 9. So these are 9 rows and 9 columns of the global matrix. For the first element, since it is defined between the global node 1 and 2, its contribution will go to the first 6 rows and columns. So whatever we did in the previous slide, that is here this transformed stiffness matrix which has 6 rows and 6 columns, these will go to the 6 rows and columns of the this global matrix. So if you again, it's more like copying the things again. So here what you will have is let me write so here you first row and first column will go to this particular location, and then this is 0, this is minus 6ei by L square, and then you have minus 12. You have basically you are copying the transformed stiffness matrix of the first element into first 6 rows and columns. So that you need to do. So minus 12 ei by L cube, and then again 0 minus 6ei. I am poor in copying, so it takes a little longer. So this is the first row, and then the second row is 0 Ea by L. Now you actually try yourself, minus Ea by L and 0. So this is the second row. Then the third row is minus 6ei by L square. Is that third? Yeah, okay. Then you have 0 here, and then 4ei by L. You are again copying that, okay, 6ei by L square, and then 0, 2ei by L. So this is the third row. Then the fourth row is 1, 2, 3, 4. So minus 12ei by L cube. Here you will have 0. Then 6ei by L square, 12ei by L cube. You're just putting that here, and then 0, and then this is 6ei by L square. I just want to demonstrate you the assembly. So here 0 minus Ea by L, 0, 0, Ea by L and 0, and then the last is minus 6ei by L square, 0, 2ei by L, then you have 6ei by L square, and then 0, and finally 4ei by L. So this is the contribution to the global stiffness matrix from the first element. Now if you take the second element if you see, it is defined between the global node 2 and 3, that is this node and this node. The degrees of freedom corresponding to this global degrees of freedom are degrees of freedom number 4, 5, 6. Corresponding to this, the global degrees of freedom are 7, 8, 9. So the contribution of the second element will go to row number 4, 5, 6, 7, 8, 9, and similarly the columns 4, 5, 6, 7, 8 and 9. And the stiffness matrix for the second element is going to be same as what you get in the local coordinate system. So that stiffness matrix, if you look at the first row of that, yeah, I think so. I have written somewhere, although it's a simple to write, but I thought I have written it somewhere, so I just wanted to make use of that. So now the first row and first row of the second element will go to fourth row starting from fourth column. So the first row is EA by L 0 0 minus EA by L. So we'll go here, one contribution will come to this location EA by L, then here plus 0 and here also plus 0, and then you are going to have minus EA by L and then 2 zeros. I think the space is little less here. Then the fifth row will, I know the second row will go to the fifth row starting from the fourth column, so that is from here. So here it is plus 0 and here it is plus 12 EI by L cube, and then here plus 6 EI by L square, and then 0 and minus 12, I hope you followed L cube, and then one more term here which is 6 EI by L square. I am writing outside that bracket. And then the third row will go to the sixth row starting from fourth column. So that is here again plus 0, and here you have 6 EI by L square, then plus 4 EI by L square. That means no, you are basically adding to these already what are existing here. So this is added with this 4 EI by L, and then here you will get 0, and then you have minus 6 EI by L square, and then one more term is 2 EI by L. So pardon me for writing outside this bracket here. So then that's the sixth, and then the next row will go to here, seventh location. So that is starting with the fourth column, and that is minus EA by L 0 0 here, and then EA by L 0 0. So then the next one is again, so it goes into this 0 minus 12 EI by L cube minus 6 EI by L square, then 0, then 12 EI by L cube, and minus 6 EI by L square. And the last one again 0, 6 EI, symmetric actually, so L square 2 EI by L 0 minus 6 EI by L square, and 4 EI by L. So this is what you get. And wherever no, there are nothing, so those are actually 0. Initially you actually initialize this matrix to 0 if you write a code for that same thing. So you get 0 0 0 0 0 0. So this is the assembled stiffness matrix, which is straightforward. It's the same as what we were doing earlier. Only thing is now at each node you have 3 degrees of freedom, and total for the element 6 degrees of freedom, and accordingly you are doing the assembly. Of course you should also be able to assemble, if I make the third node as second and second as third, so that switching over you should be able to do. Now if you look at the load vector, this is the external load vector now coming to this. So for the first element it will go to the first basically 6 rows, which is here minus Q naught into L by 2, then it is 0. We have already looked at this transformed load vector QL square by 12, and then we have again minus Q naught into L by 2, 0, and minus Q naught into L square by 12. So this is the contribution of the first element. Now for the second element, what would be the contribution? Load vector. For the second element, see, if you see, there is only distributed load again along the y direction. This is your Q naught, but it is in the negative y direction, so you will have to put a minus sign. So when you assemble the load vector, it will, for the second element, again you will start from the fourth row. So 4, 5, 6, 7, 8, 9 rows the contribution will go. So this is first row, second row, third row, will start from here. The first is 0 because there is no axial force in that. This is minus Q naught into L by 2. This is, if you look at here, because load is negative, so it becomes minus Q naught L square by 12. Then this is 0, and again this is minus q naught into L by 2, and that becomes minus minus plus q naught L square by 12. Because for the second element q naught is in the negative y direction, so I am putting a minus sign here. As you see, the axial direction there is no force, so this is 0. This is minus of q naught L by 2, because this q naught is in the downward direction. This is also because of that there is a minus sign. This is 0 0. So this is the in this case the load vector. Blue color is contribution from the first element, red color is the contribution from the second element, going into the 4th, 5th, 6th, 7th, 8th and 9th rows basically. Then coming to the internal load vector. So internal load vector, we need not actually do the transformation. Finally what we can say, because the transformed load vector will give us the forces with respect to global xy. So we can directly, if you look at the first node here for the first element, the outward normal here is along negative global y direction. So there positive forces are going to be along negative coordinate direction, and in the element level equation there would be negative forces because they are along the negative displacement directions. So I can take this force here as my at first node first element, so Fx first node first element, then minus F, this is I am putting subscript a small xy, means the forces along global xy direction. So first node first element, and the moment is, let us say, first node first element. This is the contribution from the first node. Then for the second node, outward normal is along positive y direction here, so the positive forces are going to be along positive coordinate direction. So in the element level equation there would be positive forces as we have seen earlier. So this would become Fx2 for the first element, Fy2 for the first element, and M2 from the first element. So this is the internal forces. Now without doing the transformation, I have assume that the transformed forces are forces along global x direction, global y direction, and moment about z axis. And although they would be in terms of, obviously, if you want, you can T transpose into F internal, you will get the relationship between these forces along the global xy directions in terms of local capital X and Y direction. Then when you look at the contribution of the second element, it would be starting again from the 4th row. So here we will have for the now second element first node. So I am still using the same convention. Here we will have minus of Fy for the first node of the second element, and here we will have M1 for the second element, and then here we will have Fx2 for the second element, Fy2 for the second element, and M2 for the second element. So superscripts are element numbers, subscripts are global local node numbers. So because we are dealing with two noded elements, so local nodes are always 1 and 2. So that is how I have been using the convention for the internal load vector. So this is now your assembled system level equation. So this is your global stiffness matrix, what we call. This is the vector of global unknowns. So basically 9 in this case, this is the global external force vector, and this is the global internal force vector. Is this okay? Actually the problem is simple but bit lengthy. So if you understand, then you would appreciate the other more complicated problems in 2D. So now coming to the boundary conditions, and see ultimately when you actually solve problems, you are not supposed to, more complex problems means you will have to write a computer code and do that. So you have to write the code for all of these, so that computer automatically does all this and finally gives you the solution. So like if I say that discretize this into 2 elements, this also into 2 elements, so then you can imagine the amount of calculations and work involved. So obviously it cannot be done manually, one has to do using computer code. So I am demonstrating the whole process just using 2 elements. So now what are the boundary conditions here? The problem at hand we took, we said basically this end is fixed, this end is fixed. So fixed means at node 1 and 3, global nodes 1 and 3, all the displacements and rotations would be 0. So u1 is equal to v1 is equal to theta 1 is equal to u3 is equal to v3 is equal to theta 3. These are all actually equal to 0. Okay, so that's one at node 1 and 3 because both the ends are fixed. So the global displacements along global x, y rotation about z, they are going to be 0. Then if you look at node number 2, so you will find this particular node there is no concentrated force and moment. If there was a concentrated force and moment, then the difference of these internal forces coming from the first and second elements would be equal to those forces. So for the problem at hand, there are no externally applied concentrated forces and moments at node number 2. So these would be 0 as we did earlier. Now if you draw the free body diagram of the node, taking a section just left and right of that, so you will have x21 minus fx12 equal to 0. You will have fy21 minus fy12 equal to 0, and you will have m21 minus m12 equal to 0. If let us say there is a force at node 2 along global x direction, let us say there is some force px, and along global y direction there is a force py, then this would be equal to px, this would be equal to py. If there is a moment about positive z axis, this would be actually equal to m. But for the time being, there are no forces and moments, I am putting it 0. So after these boundary condition, if you look at, we have got 9 equations for the system, and the unknowns are now, because these are already 0, so unknowns are 1, 2, 3, these are unknowns, and then these reaction forces, now 4, 5, 6, 7, 8, 9. So we have got 9 equations and 9 unknowns. We can solve for these. So again, as we did earlier, first we can take equation 4, 5 and 6 to solve for these unknowns u2, v2 and theta 2. See, it is not necessary that these are always 0. You can have, say, there is a sinking of the support. So maybe this u1 is some non-zero value. So you can still take the 4th, 5th and 6th equation, but in the in these equation when you multiply, say the first one with the value of u1, which is a known quantity, will transfer that to the right hand side. So that is the only thing you will have to account for if the boundary conditions are non-zero. In this case we are saying equal to 0. They can be non-zero also. So then to solve for those unknowns, you just take the 4th, 5th and 6th equation, and if you look at those 4th, 5th and 6th equation, what we have is essentially finally we are left with a 3 by 3 matrix in terms of those 3 unknowns u2, v2 and theta 2, and is equal to the right hand side. What we will be left with is this minus q naught L by 2 minus q naught L by 2, that's the 5th row also, and then this is minus q naught L square by 6, because it is 12, so you get basically 6. And this side what you have is basically this is the first one, so 12 no, I am not going to copy the whole thing. 12 L cube plus EA by L, that's the 4th row, 4th column here. Then you have got in between this 0 and then 6 EI by L, so 0, 6 EI by L. So this is the 4th equation, because u1 b1 theta 1 and u3 v3 theta 3, they are 0, so they do not contribute anything to the right side. Then similarly you take the 5th row here. 5th row, the first term is actually 0, and the second term is same as this, because that is EA by L plus 12 EI by L cube. So essentially 12 EI by L cube plus EA by L, and then this is again 6 EI by L square. And the last row is now your 6th row, which is this is 6 EI by, I think that is L square here. Yeah, this is also 6 EI by L square, and then we have again 6 EI by L square, that you take care, and this is 4 EI by, no, that was 4 EI by L, not L square, so please make that correction. So it becomes the last one here becomes 8 EI by L. Okay, so now these are 3 equations. Of course we will have to solve these. So the solution of these 3 equations would give you u2, v2 and theta 2. You need to solve, of course, these equations. And I also wanted to demonstrate you that subsequently how we do the post processing to calculate the displacements within the element and also the stresses. So now let us also look at, so this solution, you have to solve these 3 equations. Maybe what you can do is from the first equation you can express say u2 in terms of theta 2, and from the last equation maybe you can, you can make use of from the second equation, you can express maybe V2 in terms of theta 2, then solve from the third equation theta 2, and then come back solve for U2, V2 manually, of course. That is what one way you can do. Now let us look at post processing. Yeah, is there anything missing? I think I wrote correctly. This is 0. Yeah, this is 0. Yeah. Is not? See, because the Z axis, local and global, they are same. So what you're doing when you look at the, let's say, the first element. Now in terms of global system, if I look at the first element, this is my first node, the second node, this is my global x axis, and this is my global y axis, and Z is coming out of the board. Since outward normal here is along negative y direction, so the forces and cross-sectional forces are taken positive along or about the global x, y and z axes. So as far as the force along x direction is concerned, I would show that force as Fx1, that is what I have shown, and then the force along y direction as Fy1, and the moment is your z axis. See, your z axis is coming out of the board, and that means the positive moment about z axis would be like this, but I am taking a moment like this. As far as the now rotation are concerned, with respect to global z axis, a positive rotation like this. So that would be a negative moment. So that is what we have shown here, that this is x, y, so z is coming out like this. So positive moment here, this is your actually m1. Same thing when you try to show the internal forces with respect to global coordinate axes at node 2 of the first element. Outward normal here is now along positive y. So the forces and moments would be shown, cross-sectional forces and moments, positive along or about positive coordinate directions. So now here along x direction you will have Fx2, this is along positive x direction, Fy2, this is along positive y direction, and then moment is, this is the moment m2 about positive z axis. And see, in the load vector, when you see with this convention, in the load, it's a very good question actually. So if you look at in the load vector, you see as far as the global displacements are concerned, we are taking u1 along this global x direction, we are taking v1 along this global y direction, and the rotation we are taking positive along z axis. So this is my theta 1. Same way here, my u2 is in this direction, v2 is in this direction, and my theta 2 is in this direction. So in the load vector on the right hand side, because this force Fx1 is in the negative direction of u1, similarly this force is along negative direction of v1, and this moment is along negative direction of the theta 1. So in the load vector they are here coming as minus, so minus Fx1 minus Fy1, and this is also minus here. I'm sorry, I missed this minus sign. Please make that correct. I think you were pointing out to that. Okay, thanks. That was, this has to be minus. And if you look at these, this one, and this one, they are shown as positive because they are the forces and moments along the positive displacement directions. So on the right hand side, if the forces are positive, they would be positive. That means if the forces are along positive displacement directions, they would be positive. If they are along the negative directions of positive displacement, so then they would be negative. So that is how this has to be minus there. This is minus here, and same thing here. I have put minus sign here. So maybe I just missed that minus sign there. Okay. So then now post processing I was talking about. So then post processing means now let us take the first element. So let me take element number 1. This is my element, this is my node 1, local and also of course corresponding global nodes, and the coordinate system, we already know that the local element x axis is this, and this is my local y axis, but the global coordinate directions are, this is your x, and in this you have your actually y. Now what we want is, see, because when you want to get these stresses, you need to differentiate in terms of the the minimum cross section, minimum cross sectional properties, we will have to calculate the stresses and strains with respect to local coordinate system of the element. So what I would need is say epsilon xx, that means with respect to global coordinate, local coordinate x, epsilon xx as per the derivation we did, this is du naught by dx minus y times d2v by dx square. And what is u naught in the local coordinate system? This was actually n1 into u naught 1 plus n2 into u naught 2. Where you make please see that this is a small u naught and this is small u naught 2. That means these are the displacement with respect to local element x axis. And similarly, if you remember, v was taken as h1 v1 plus h2 theta 1 plus h3 v2 plus h4 theta 2, isn't it? So now what I have after the solution, I have got this displacements with respect to global coordinate axes u2 v2 theta 2. So before I can actually calculate this u naught or its derivatives, I need to get u naught 1, u naught 2, I need to get v1 theta 1, v2 and theta 2. So again you need to go back to the transformation. So the transformation is what? We know that is small d, which is nothing but for the first element u naught 1 v1 theta 1, u naught 2 v2 theta 2 from the transformation. This is nothing but in terms of your transformation matrix which was there here, that t, and into the your displacement with respect to global degrees of freedom. Here they are u1 v1 theta 1 for the first element, u2 v2 and theta 2. And of course for this particular case you would find that if you put this t transformation matrix and multiply this, so finally this result comes out. I mean, you can just cross check. So finally what you get, already this is 0, we know that this is 0, this is 0 from the boundary condition. So what you have is this. So these come out as basically for the first node, obviously they have to be 0, because if the displacements in any two orthogonal directions are 0, so they would be 0 with respect to any other coordinate directions. So they would be 0 to displacements as well as rotation, but this becomes v2, this becomes minus u2, and this remains theta 2 after the transformation for the first element. And again I know that can be physically interpreted, because with respect to local, now my if you look at the local x-axis is same as global y-axis. So then the x displacement, local x displacement would be equal to global y displacement. So that is what you see here, that for the second node, local displacement for the second node is equal to global y displacement, and whereas the local y-axis is along the negative global x-axis. So you get the displacement, local displacement along y direction is equal to negative times of the displacement along global x direction. You follow this? Why this? It can be, although it is directly coming from this node multiplication, but you can physically also interpret these. So once you do this, that means you are calculating now your u naught 1 is 0, v1 is 0, theta 1 is 0, u naught 2 is equal to capital V2, which you would have solved, and v2 is equal to minus u2, and theta 2 of course is equal to theta 2. So then you can write your u naught is equal to n1, which is 1 minus x by l, into u naught 1, which is 0, and plus n2, which is x by l, into u2, which is actually v2. So then you get this as x by l into v2, which is displacement along global y-axis at node 2. Similarly, if you look at v, would be as you see that v1 and theta 1 they are 0, only what you have is v2 and theta 2. So you will have minus h3 because of this minus into u2 plus h4 into theta 2, and h1, h2, h3, h4 expressions are there already with you with in terms of local x-axis, element x-axis. So once you have got this, then to calculate the strain, what you need is the first derivative of u naught and second derivative of v. So what you can do is, of course, if you want to calculate the displacement along the length of the member at any given location, you put that corresponding value of capital X and you can calculate that. Similarly, in this, if you put the value of X, you can calculate v anywhere within the element in this expression. Then du naught by dx would be simply, as you see here, 1 by L into V2, and d2v by dx square would be no, minus d2h3 by dx square into u2 plus d2h4 by dx square into theta 2. So from this you can calculate, let's say at the center of the element, or maybe at first node itself you want to calculate the stress, so then you put capital X equal to 0. So this remains this derivative remains same because it is independent of capital X. This would be, these derivatives are going to be linear functions of capital X. So you calculate these, and then you calculate your strain. Then finally stress sigma xx would be E times your epsilon xx, which would be E times du naught by dx minus y times d2v by dx square. So you would have calculated all of these from this, and then you can calculate the stress, and then of course maximum stress would be at top and bottom, so you can put y equal to plus or minus h by 2 depending on the cross section. So this is how you would do the post processing calculations for the first element. For the second element it is straightforward, because in this particular problem the local element coordinate accesses for the second element and global, they are same. So you similar kind of a formula you would use directly. So that is, see, when you are going for the element 2, again for the element 2, if you look at u naught anywhere within the element is going to be 1 minus x capital X by L into, it is going to be directly u2 which is non-zero, and u3 which is actually plus x by L into the u naught 2 which is actually equal to u3, and u3 is 0, so this into 0. So 1 minus x by L into u2. So this directly I have written. Then similarly v would be going to be h1 into, it would be capital V2 plus h2 into theta 2. And for the third node, which is local second node of the second element, since the v and theta they are 0, so this is what you will get, h3 into 0 plus h4 into 0. And once you got this, now this x is again local coordinate for the second element with origin at the the first node of the element. So for the, when you are talking about the second element, capital X is having origin here, so it's 0 here, and it is equal to length of the element L at the second node, which is global node number 3. So you can calculate by putting the appropriate value of capital X here and calculate the displacements, strains and stresses. So this is how you do the post processing. Of course you can always calculate the reaction forces at node 1 and 3 using the first 3 and last 3 equations from the global system equations. So this is what I wanted to demonstrate you. Now you need to solve the similarly the 3 problems I had given in the last class. That is actually a home assignment for you, so you must solve those. So I think next I wanted to start Timasenko beam element. So maybe I'll just give you a brief background, and then I'll start actually in the next class. So far what we have done, we have assumed that normal to the middle surface or neutral surface remains normal after the deformation of the beam. Now we are going to relax that. So what I am saying here, that if you have, let us say this as beam, and still let us say talk in terms of local coordinate system x and y. I think okay. I'll just briefly only talk about this Timasenko beam theory. So this is your, let us say the neutral axis, and if you consider a normal to the neutral surface in the undeformed configuration, so let us say this is the normal, and then this deforms, and in the deformed configuration, let us say this beam takes a shape like this, and this is the deformed neutral axis like this. Now when you look at this line, which is initially normal perpendicular to this axis, this now if I draw at the same point the tangent here, so one thing I will have is, say, normal to this tangent here, that normal is this. But now see, in the Euler-Bernoulli beam theory we said that actually this actual line drawn perpendicular to this line coincides with this normal to the tangent drawn here to the middle surface. But when we relax that condition, So this green line is still normal to the tangent drawn at this location, but actual line here, which is this cross sectional line, will not coincide with this, but would be at some angle. So let us say that angle is something like this. So now this line is no longer along normal, but it is at some angle, and this consider this normal, which is not remaining normal to the deformed surface after the deformation, we call the corresponding theory as Timošenko beam theory. So the assumptions here are that now normal to the middle surface, or you can say neutral surface, does not remain normal to the same surface after deformation. Whereas in the Euler-Bernoulli beam theory, we said that it remains normal, and therefore obviously it is applicable for thin beams. So that is what we had said. So normal remains normal after deformation. Of course, the second assumption is still that we are assuming that this line, which is initially straight, remains straight after the deformed configuration. So second thing is that the plane sections remain plane. This was there in the Euler-Bernoulli beam theory also. So plane sections remain plane after deformation. So these are the two assumptions, and I stop here. We'll continue in the next class further onto this formulation of Timošenko beam finite element. Yeah, it's a tangent to the neutral axis. If you have any doubts or questions, you can ask outside. Yeah, Timošenko, then I will be starting with two-dimensional problems. You are going somewhere?
Yes.
Yeah, and you will have to then take notes from somewhere.